Here's a problem that illustrates several of the concepts we've learned about the kinematics of particles. And let's take a look at our problem here. We've got this block starting at the top of the ramp. It weighs 25 pounds, and we're told that this will slide without friction to the bottom of the incline, where it collides with the second block, which weighs significantly less, 5 pounds. And the coefficient of restitution for the impact is 0.4. After the collision, this block B will slide along with a coefficient of friction, in this case kinetic coefficient of friction of 0.25, and when it gets to the end of the ramp it will become a projectile and land on this lower surface. So what we're trying to find out is how far along will the block B land. What is the distance d here? So a couple of dimensions we need to know. In the first case, the block its center of gravity will fall by a total of 6 feet. Block B will slide 6 feet along the horizontal surface with friction, and then will drop 3 feet onto the lower surface. So our first thing, order of business, is to find how fast block A is going to be going just before it collides with block B. So what method should we use here? Well, the fact that there's no friction probably will lead us to do conservation of energy. So usually when there's no friction involved, no unconservative forces, conservation of energy is the easiest method to use. And in this case, actually, it's the only method we can use because we don't know anything about the geometry of the ramp. If we did have friction, then we would have to know how far the block actually slides. But in the case of friction-free, then we don't really need to know that. All we need to know is how far it drops, which is the 6 feet. So initially we start out at rest, so the kinetic energy is 0. Potential energy, if we call the datum as shown here, we're 6 feet above that, so the weight times the distance is 150 foot-pounds. Our final kinetic energy is 1/2 mv squared, v being what we're trying to find here, and the final potential energy, because of where we set the datum, would be equal to 0. So setting the initial energy equal to the final energy, and we can solve for v, which in this case is 19.6 feet per second, right before we collide with block B. Okay. Now, our next step, after the collision, how fast is block B going to be going? And what method do we use here? Well, whenever we have an impact, what we use is the conservation of momentum. And along with that, we have a coefficient of restitution defined, so we have to use that as well. In the case of impulse and momentum, the time of the impact is oftentimes needed, but because of the fact that you have the coefficient of restitution defined, the actual duration of the impact is not needed in a problem like this. So right before impact, we just calculated the velocity of block A, and block B is at rest in this case. And after the impact, well, we're trying to find the velocity of both blocks. So we have two unknowns, which is why we have to combine the equation for conservation of momentum with that of the coefficient of restitution. So by our equation from the conservation of momentum, entering the things that we do know here, and in this case the g will cancel out from all the terms, we don't actually have to enter that in, but what we get is an equation for one of the final velocities in terms of the other. So we have VA after the collision as being equal to this formula that we have here, which includes the velocity of B right after the collision. So we'll use this along with our definition of the coefficient of restitution. So plugging in our known values again, and you notice here for the velocity of A after the impact, we've put in the equation that we just came up with from the conservation of momentum. So solving this for the velocity of B, we come up with about 23 feet per second as being the velocity of block B just after the impact. And although we don't need it for the problem, we might want to look at what the velocity of block A is after that impact. And so we see it's slowed down from its 19.6 feet per second down to a little under 15 feet per second after the collision. Okay. Now block B is going to slide along the horizontal surface with friction. So because of the fact we have friction involved, then using work and energy is the logical choice here. Now we could just use the equation of motion, but we have to calculate the acceleration. So it's just one more step. It's not a very difficult step, but work and energy lets us actually bypass that. So in this case, we know the initial kinetic energy. We're trying to find the final velocity, and in between we know that the only force that's doing work on the particle is friction, and so the work done from the initial state to the final state is minus the friction force times the distance through which it travels. And so plugging in again our known values into that, in this case we do have to bring in the value of g is 32.2 feet per second squared to be able to convert our weights into masses. And this middle term here that you can see is the coefficient of kinetic friction times the normal force, which is equal to the weight in this case, times the distance through which it acts. And again, it's doing negative work on the system. So we find that the velocity is slowed down from about 23 feet per second to a little under 21 feet per second. It's not going very far, so the velocity change isn't terribly great. And now we're ready to figure out how far out this is going to go when it becomes a projectile. So in the y direction, we know that the acceleration is simply g downward. And so integrating that twice, we get an expression for the value of y. And we know a lot of these things except for the value of time, so we can actually solve this for time and find out that it's going to fly through the air for about 0.43 seconds before making its landing. In the x direction, then there is no acceleration, and so again integrating that twice, and we have the initial velocity in the x direction is simply the velocity that we found from step 3. And so plugging in the time that we got from the previous step, we find out that the block should land about 9 feet onto that lower horizontal surface. Okay, so let's go and look at the simulation now. And in the first case we're going to run is the baseline case we just analyzed. And so here's our collision, and we can see that the block does land about 9 feet down. Now obviously we're treating these as particles, but in our simulation we probably do get some rigid body motion there as well. So again, just our assumptions are never perfect in these simulations. Let's take a look at the velocity of block A first. And so we can see that these match up pretty well with our calculated results. We're slightly under 20 feet per second right before we make the collision, and at about 15 feet per second after the collision. Block B shows again it being at rest until right at the collision here. You see about at 22 feet per second, and that drops by not a whole lot, but a couple of feet per second before it flies off into space here. Now, we do have two other studies here to show as well for two different coefficients of restitution. In this extreme case, the coefficient of restitution is equal to 0, and so you can see what happens here is the two of them travel together. That's the case where you get the most energy lost, and you can see that those landed at a much lower, or excuse me, much shorter distance, out about 6 feet. And the other extreme is if we set the coefficient of restitution equal to 1, and that's going to be where energy is going to be conserved as well, and you can see that second block flies all the way out to about 12 feet.